In this video, we're going to be looking at finding the antiderivative of a composite function. Let's start off by thinking back to when we took derivatives of a composite function. So for instance, if I had a composite function f of g of x, and I wanted to find the derivative. We learned the chain rule, which says we take the derivative of the outside function, leaving the inside function alone, times the derivative of the inside function. So if we want to find the antiderivative of f prime of g of x times a g prime of x, since this is the derivative of this function, when we try to find the antiderivative of this, we should get this function back. So we should get, this should be some f of g of x, plus we could have had some constant of integration. Now what we're going to do with U substitution is we're going to let u equal our inside function. So say we're given this integral right here to solve. Let's let u equal g of x. So we're going to replace our g of x's here with u. And then we're going to replace, we will let, taking the derivative here, but writing it in differential form, g prime of x, if I wrote this as du dx, I'm just simply taking the derivative, but I want to write this in differential form. So we're going to write this in differential form, so we're going to put the dx on the other side. That's differential form. So we would have this. So now we're going to replace everything in this integral in terms of u. So we would have f prime of, now we're replacing g of x with u, and then g prime of x dx, g prime of x dx is replaced with du. And so that should equal, and again we're going to replace our g of x with u, so we'd have f of u plus our constant of integration. This is the idea behind U substitution. We're going to identify the inside function as u, take the derivative, and then rewrite our integral in terms of u, and then we can find the antiderivative many times. So let's try that. So we have this integral. So let's identify our inside function u. Oops, keeps jumping. Let's try it again. Okay, so let's identify our inside function u as x to the fourth plus 2. So we take our derivative, but we write it in differential form. So we'd have 4x cubed, and then we would have dx. Now we're going to replace everything in this integral here, this integrand, in terms of u. So we'd have the integral of, now look up here where we have cosine of x to the fourth plus 2. I'm going to replace x to the fourth plus 2 with u. So now we just have to replace dx and x cubed. Notice down here we have dx x cubed. We don't need that 4, so we can divide the 4 to the other side, and we're just left with x cubed dx. So now we can replace x cubed dx with du over 4. So you'll notice here we have everything in terms of u, but if we replaced u, we would have our cosine of x to the fourth plus 2, that's cosine of u, and then du divided by 4 replaces our x cubed dx, and that's our original integrand. So let me just clean this up a little bit. I'm going to pull this 1/4 from here, the du over 4. It's just a coefficient, so I can pull it out front. So we have cosine of u du. Now we can find the antiderivative of the cosine of u in terms of u. We know the antiderivative of cosine of u is the sine of u, and then plus our constant of integration. So we would have 1/4. Now we need to get our u back into terms of x. So we look back here at the relationship we built. We said u equals x to the fourth plus 2. So we're going to replace u with x to the fourth plus 2. And now we're back into terms of x. And we have our antiderivative. Now if you took the derivative of this, you should get back what we have in our original integrand. That's how we check to see if we have the correct antiderivative. So if you took the derivative of this, you would see we would get back our x cubed cosine of x to the fourth plus 2. That's called U substitution, this process. Let's try another one. So for this one, let's let u equal 2x plus 1. So du would equal 2 dx. And we can see that in our original integrand here, we don't have this 2 that we need to replace, so I'm just going to divide that. And now we're going to rewrite our integral. So we would have the square root of u times du over 2. Now you can see that this right here is equivalent to the square root of 2x plus 1. Our dx, this here, our dx here is replaced with du over 2. So that's how we replace everything in terms of u. Now we can find the antiderivative. We know that the antiderivative, let's just rewrite it first. The square root of u is u to the 1/2, and I'm going to pull the 1/2 out front from the du. So we have 1/2. Now we're finding the antiderivative, so we add 1 and divide by that same power. So we'd have to the 3/2 divided by 3/2 plus our constant of integration. Now dividing by 3/2 here is the same if we just invert and multiply, the same as multiplying by 2/3. And now we're going to replace our u. We know that u equals 2x plus 1. So that's what we're going to replace our u with. 2x plus 1 to the 3/2 power plus c. And so we could reduce the 2's here, and we have 1/3 times 2x plus 1 to the 3/2 plus c. And that's our antiderivative. Our next problem. Let's let u equal 2x plus 1. So taking the derivative, we would get 2 dx. And then I can see we don't need that 2, so So I'm going to divide that over. Now, when I start making the replacements, looking at my original integral over here, I would have in the denominator the square root of u. That would replace the square root of 2x plus 1. Dx here is replaced with du divided by 2. But notice we haven't replaced this x. So we're going to go to our relationship here, and we are going to solve for x. So we're going to subtract 1 from both sides and then divide by 2. So we'd have u minus 1 divided by 2 equals x. Now we have a way to replace x in terms of u. We would have u minus 1 divided by 2. I'm going to invert and multiply, so we'd have u minus 1 all over 2 square roots of u du, and the 1/2 I'm going to pull out front. And now this 1/2 I'm going to pull out in front as well. So we'd have u minus 1 divided by the square root of u du. And then let's rewrite this by dividing each term in the numerator by the square root of u. So this would become, now u divided by the square root of u is u to the 1/2, and then the next term is just going to be u to the negative 1/2. Now taking the antiderivative, we're going to add 1 to the exponent. So if we add 1 here, we would have u to the 3/2 divided by 3/2, but we know that's the same as multiplying by 2/3. And the next term, we have u to the negative 1. If we add 1, which is adding 2 over 2, I just get a common denominator. That would be u to the 1/2 divided by 1/2, which is the same as multiplying by 2. Then we would have to add in our constant of integration. Now since I'm running out of room there, let's move back up over here. So we would have 1/4 times 2/3, and then u to the 3/2 minus 1/4 times 2 u to the 1/2 plus c. So let's do a little reducing here. So we would have 1/6. Now u we know is 2x plus 1. So let's make that replacement. To the 3/2 power, that's replacing this, minus, now let's simplify 1/4 times 2. So we would have 1/2, and then again we're going to make the replacement for u is 2x plus 1 to the 1/2. So that's this piece, oops, I circled the 2, but that's this piece here plus our c. So if we're given an integral in radical form, typically we give it back in radical form. So we would have the square root of 2x plus 1 cubed over 6 minus the square root of 2x plus 1 over 2 plus our constant of integration. So there is our antiderivative. Okay, let's try this one. Now for this one, let's let our u, our inside function, be 5x. So du would equal 5 dx. And I see in the integrand we would not need that 5, so I'm going to divide it across. And then I'm going to rewrite our integral in terms of u. So e to the u would give us e to the 5x, and then dx is replaced with du divided by 5. And I'll bring the 1/5 out front. And we know that the antiderivative of e to the u is e to the u. So we would have 1/5. Now u is 5x, so we're going to replace u with 5x, and we have our antiderivative. Okay, our next example, let's let u equal 1 plus x squared, our inside function. So du would equal 2dx. And up here I see I don't have to replace a 2, so I'm going to divide by 2. So we'd have x dx. So at this point, let's see what we could replace. We would have the square root of u. Now that is replacing this piece here. Now we could replace x dx. So let me rewrite. If I rewrote our integrand as this, x to the 4th times x times dx, because I can see I could replace my x dx with du over 2. So this would be replaced with du over 2. So that would be my du, whoops, let's get the same color. So that would be our du over 2. But notice we have not replaced the x to the 4th. So how are we going to replace our x to the 4th? Well, let's go back to our original substitution and solve for x to the 4th. We can see that if we subtracted 1, we'd have u minus 1 equals x squared. So if we squared both sides, we'd have u minus 1 squared equals x to the 4th. So that's how we can replace x to the 4th, with u minus 1 squared. So we'd have u minus 1 squared. And now we've replaced everything in terms of u. Let's multiply this quantity, let's expand, into u squared minus 2u plus 1. And let's bring the 1/2 out front. And then let's multiply the square root of u through the parentheses. So this is u to the 1/2. And when we multiply this through the parentheses, we know we would add the exponents. So u to the 1/2 times u squared. That would be u to the 5/2 minus u, see I'm just multiplying these together here, and then we would have minus 2u, when we add our exponents we'd get 3/2, plus u to the 1/2. Now we can find the antiderivative term by term. So we'd have 1/2. Here we would have, we're going to add 1 to the exponent. So we'd have u to the 7/2 divided by 7/2, or if we invert and multiply, minus 2 times. Now when we add 1 here, we'd have 5/2. So u to the 5/2, but we would invert and multiply, so we'd have times 2/5. And then here, adding 1 to our exponent, u to the 3/2, and then times 2/3. So when we multiply these together now, we've got to multiply this 1/2 through to each term. So we have to remember to do that. So when we multiply by the first term, we'd get 2/14, so it would reduce to 1/7. And u is 1 plus x squared. So let's make that replacement to the 7/2. So that's replacing this one. Minus. Now we have 4/5 times 1/2. So that would reduce it to, so we'd be left with 2/5. And again, we're going to make our substitution to the 5/2. That's replacing this one. And then plus. Now 1/2 times 2/3 would leave 1/3. And then again, replacing u with 1 plus x squared to the 3/2 replaces this. And there's our antiderivative. Okay, let's find the antiderivative of the tangent of x. What we're going to do here first, before we look for our inside function, let's rewrite this as the sine of x over the cosine of x. Now let's let u be cosine of x. So du would equal negative sine of x dx. So when we make our replacements into our integral in terms of x, now we're going to write it in terms of u. Now notice we don't need this negative, so let's multiply both sides by -1. So sine of x dx is going to be replaced by negative du. I'm going to pull the negative out front, and then cosine of x is going to be replaced with u, 1 over u. Now we know that the antiderivative of 1 over u would be the natural log of the absolute value of u plus our constant of integration. And then we make our substitution. U we let equal cosine of x. So we'd have cosine of x. And there's our antiderivative. Now you could use properties of logs to rewrite this as. Now this does mean 1 all over cosine of x. It's not the arc cosine. And so if we simplified that, we could write it as ln of the absolute value of the secant of x. So there's two different ways you could write the antiderivative of tangent of x. Either way is fine. Okay, now we're going to move to a definite integral. We evaluate a definite integral the same way as a indefinite integral. We find the antiderivative the same way. It's just that we have to apply the fundamental theorem when we evaluate it now. So let's let u, our inside function, be 2x minus 1. So du would be 2 dx. And I see we don't need the. Now if we would have had up here 2 times this quantity, then we would have left the 2, because then we could have replaced 2 dx. That's what I mean by when I say we don't have the 2 to replace in the original integrand. So we divide that across. So our integral at this point would look like the square root of u, and then we'd have du over 2. And everything is replaced now in terms of u. Now I'm not going to write the upper and lower limits of integration. Okay, here, I'm not going to write those in, because if I go from 0 to 4, that's if I'm in terms of x. But here, I'm in terms of u. So I do not write the upper and lower limits of integration until I get this back into terms of x. So if we rewrite this as u to the 1/2 du, now we can find the antiderivative. We're going to add 1 to the exponent and divide. So we'd be dividing by 3/2, which is the same as multiplying by 2/3. Now we do not need to write plus c, our constant of integration, because when we apply the fundamental theorem, we saw that those c's would just cancel out. Now if we reduce, we have 1/3 u to the 3/2, and now I'm going to make the substitution. U equals 2x plus 1, and that would be raised to the 3/2 power, and now I can say I'm going to evaluate this from 0 to 4. So if we apply the fundamental theorem, we have 1/3 times, we're going to plug in 4 first, plus 1 minus 2 times 0 plus 1, and each of these are raised to the 3/2 power. Let me erase that so it doesn't get confusing here. Let me put that up a little bit higher. So this was from 0 to 4. Now this is the 3/2. So we have 1/3. Now this quantity here is just 8 plus 1 is 9 to the 3/2 minus 1 to the 3/2. So we have 1/3. Now this is the square root of 9, which is 3 cubed, is 27. So 27 minus 1, which is 26 over 3. So there's our final answer. Now what I would like to do is show you another way to do this from here. Let me rewrite this over here. Here, if we wanted to, we could leave this in terms of u and evaluate this in terms of u instead. What we could do is go back to our upper and lower limits of integration. Here, in terms of x, we're evaluating this integral from 0 to 4. Well, if x is 0, we can use this to find out what u would equal. We would just plug 0 in for x. So we'd have 2 times 0 plus 1. So if x is 0, u would be 1 using this relationship. We can do the same thing with the upper limit of integration. If x is 4, we're going to plug 4 in for x here. So we'd have 8 plus 1 is 9. So in terms of u, we have 1/3, 9 to the 3/2, minus 1 to the 3/2. And notice, this is the exact same thing as we have down here, which will give us our 26 over 3. So we can leave this in terms of u if we change our upper and lower limits of integration to terms of u. Or we can change it back into terms of x like we did down here and just do it in terms of x and not have to worry about changing the upper and lower limits of integration. That's why I said here we don't write the upper and lower limits of integration if we're in terms of u, because these were from 0 to 4 would be in terms of x. Now if you decided to leave it in terms of u and put from 1 to 9 here, that would be fine, because we are in terms of u. You change the upper and lower limits in terms of u. That would be fine. But you can evaluate these either way. Leave it in terms of u, change your upper and lower limits of integration, or change back to x and use the original upper and lower limits of integration. Here we have another definite integral. Let's let u equal ln of x. Du then would be 1 over x dx. And you can see that to replace ln of x, we would just have u, and dx times 1 over x would be our du. And you see here we have ln of x times 1 over x times dx. So this 1 over x dx here can be replaced with simply du. So we can find our antiderivative in terms of u, which would be u squared over 2 plus our constant of integration. Oops, we don't need that, do we? This is a definite integral. So we're going to evaluate this over an interval. Now let's change this back into terms of x. So we said x is ln, changing it back into terms of x, we let u equal ln of x, so we'd have ln of x squared over 2 evaluated from 1 to e. Using the fundamental theorem, we would plug in e over 2 minus ln of 1. This whole quantity is being squared all over 2. We know ln of 1 is 0, so we're left with ln of e quantity squared over 2. And we know ln of e is just 1, so we could say this is just 1/2. Now, if we left it in terms of u, let's try that. Let's leave this in terms of u. So we could change the upper and lower limits of integration. Originally in terms of x, the lower limit of integration is 1. So if we plugged in 1 for x, we'd have ln of 1, which is 0. And then if we plugged in e, we'd get u equals ln of e, which is 1. So we would have 1 squared over 2 minus 0 squared over 2. And again, we get the same solution. Now let's think about symmetry for a moment. Suppose we have a continuous function. If f is even, let's think about an even function. We know that, oops, let me get that back. We know that to determine if a function is even, we can plug a negative x into the function, and if we get f of x back, the function is even, which means it's symmetrical about the y-axis. So it may be something that looks like this. Now, if I want to find the area under the curve, and we know this is symmetrical, and I'm going from negative a, which means this distance, to a, to this distance, those distances are the same from the y-axis, wouldn't they have the same area? Wouldn't the area from negative a to 0 be the same as the area from 0 to a? So if we wanted to find the area from negative a to a, let's call this y equals f of x. Couldn't we just as well say we're just going to take 2 times the interval from 0 to a of f of x dx? We'll just find the area under the curve here, and since we know it's equivalent to the area under the curve here, we'll just multiply by 2. Now, what if we were working with an odd function? Which means if we plug a negative x into a function and we get negative f of x, it has symmetry with respect to the origin. And let's draw a graph. If I have symmetry with respect to the origin, and I want to find the area under the curve from negative a to a, let's call this g of x, I could take and determine the area under that curve. But if we look at it geometrically, the area under the curve here would have a negative area A. Since it's symmetrical, this would be the same area, but it would be positive, so this should equal 0. So if you're working with an odd function, and you're going from negative a to a, you know the area is just going to be, the net area is going to be 0. Whereas if you're working with an even function, you could go from 0 to a and then just double it because you know you have symmetry with respect to the y-axis.